this video, I'd like to go over some of the topics in section 11.4 using tree diagrams. However, as we work through this worksheet, why did the actor jump out of a window in Times Square? We will touch on a preview of what will come in section 11.5 because two of these problems, they're the problems in number 6 here. Two of these problems are really not suitable for completing with a tree diagram. So I'll address the method of solving problem number 6 with a formula. I do want to remind you that as you do your written work for this activity, that you should have the tree diagram, and instead of 8, it'll be a total of 6 trees, and the formula written for each of these different problems. So you'll do each of these problems on the sheet using both 11.4 and 11.5. But in this video, we're only going to focus on the trees. You should be able to go back after you complete 11.5 and add the segment to the work with showing the formula. So let's start with the tree diagrams. And before we go too far into tree diagrams, I want to stop and highlight the fundamental counting principle. The fundamental counting principle tells us how many different outcomes are possible given the number of constraints or the number of ways that we can do each part of an experiment or each part of a game. So, for example, when we look at this first problem with these two spinners outlined in blue, we see that for the first spinner there's 3 different colors, and for the second spinner there's 2 different letters. So what the fundamental counting principle tells us is that there's 3 ways for the first spinner to land, 2 ways for the second spinner to land, so that means there's a total of 6 different outcomes. When we look at the second set of spinners, they're outlined in red, or it's actually a spinner and then a 6-sided die. We can see that for the first spinner there's 3 different colors, but for the 6-sided die there's 6 numbers on which it could land. So how many ways can we spin the spinner? 3 different ways, white, black, or striped. How many different ways can we roll the die? 6 different ways, so 1, 2, 3, 4, 5, or 6. So that tells us that there are 18 possible outcomes. Or in other words, the sample space for the first game is going to have a total of 6 elements. The sample space for the second game, the spinner with the die, will have 18 different elements in the sample space. I'm going to use that fundamental counting principle to confirm that I have completed the list of elements in the sample space, and also as just a point of reference to know how much space I should save on my paper. I'll show you what I mean by that. When we do these spinners, we're going to draw a tree diagram. And because I know that there are a total of 6 elements in the sample space, I know that I need at least 6 lines when I go to draw the tree. Let's start by just looking at each spinner and thinking through the probability of each outcome. The probability with this first spinner landing on red is 2 because there are 2 reds out of 5 because there's 5 different segments where the spinner could land. For white, it's also 2 out of 5, but notice for blue, the probability of landing on blue is only 1 out of 5. When we look at the second spinner, the probability of landing on A is 1 in 3, and the probability of landing on B is 2 in 3. So let's make this tree diagram. I'm going to start by listing the outcomes. Well, let me show you the before we go to the completed one. On our first spin we could get a red, white, or blue. And so to draw the tree, we draw a line to each the red, white, and blue from one starting point. So it'll look something like this. And then after we roll a red or spin a red, we could then spin an A or a B. From white, we could get an A or a B. And from blue, we could get A or B. So this is what our chart would look like. What I'm going to do next is list the sample space. I list the sample space by saying red A, red B, white A, white B, blue A, and blue B. So that's our 6 elements in the sample space. So these 6 purple pieces here are what we'd call the sample space. I could also go back to get the probability of each element in the sample space, because the probability of going to red was 2/3, white, or 2/5 rather, 2/5. White was 2/5, and blue was 1/5. And then the A is 1 and 3, B is 2 and 3. So I can fill those in on each of these lines. And notice that the first spinner and the second spinner are what we're going to call independent outcomes. What happens with the first spinner has no bearing on how the second spinner works. So these are going to be considered independent events because the 2 spinners have no bearing on how one another respond. So our first event, the red, white, or blue, doesn't affect the A or B for the second spinner. So they're called independent. Once I have the sample space and I understand the probability for each of the different pieces, I can multiply them. So the probability of this red A is going to be 2/5 times the A. So 2/5 chance of getting red. After I have red, I have a 1 in 3 chance of getting the A. So that gives me a total of 2/5 times 1/3, or 2/15 chance of getting a red and then A. Do you see how you could finish this for each of the possible outcomes, all 6 of them? We'd have 2/5 times 2/3, so that's 4/15. White and A, white and B will come out the same as we did red and white, or red and A, red and blue, B. But when I go to do the blue, I get a little bit of a difference because we have a 1/5, 1 in 5 chance of landing on blue, and then we multiply by the third and the 2/3. So 1/5 times 1/3, 1 times 1 is 1, 5 times 3 is 15, 1 times 2 is 2, 5 times 3 is 15. Now the next piece to this work is going to be for the worksheet, and to get an answer to type in, I need to divide 2 divided by 15 and round it to 3 decimal places. So let me show you how I'm rounding it. If I'm rounding to 3 decimal places, then I need to know 4 digits, and the 3 decimal places would be 0.133, and then I can change that to a percent by multiplying by 100, 13.3%. 4 divided by 15, when I round that to 3 decimal places, I'd get 2, 6, and then the third 6 is going to go up to 7. And then I can change this to a percent by multiplying by 100, 26.7 And so on. You could do the same for each of these other numbers. 1 divided by 15 is going to give us 0.067. It's approximately, not equal to, but approximately 0.067. And so I could make that a percent by multiplying by 100, 6.7%. So you should be able to finish these numbers and divide them to get the decimals and then the percents. So one more time, walking through this, the probability of getting a red on the first spinner is 2 in 5, and then an A is 1 in 3. So if I multiply the 2 over 5 and the 1 over 3, I get 2 times 1 is 2, 5 times 3 is 15, so I get 2 over 15, and so on for each of the 6 outcomes. Go ahead and pause the video to finish this list if you haven't finished it already. When we get to section 11.5, we'll see another way of doing these problems, and that's with a formula. So make sure you are aware that you'll need to come back to this worksheet. At least you can get the answers and type them in now, or you could wait until after you do them a second time with a formula, and that'll allow you to check your answers. Let's look at this next spinner. We've got a spinner that could land on white, black, or striped, and then a number cube that could land on a 1 through 6. So that spinner, we have a 1 in 5, or rather 1 in 4 chance that it lands on white, 2 in 4, which simplifies to a half, chance that it lands on black, and stripe is 1 in 4. And then after we spin that spinner, we're going to roll the die. Notice that these are independent events again. We call them independent events because that spinner has no effect on the 6-sided die. You should be able to write the whole sample space out: white 1, white 2, white 3, so on. Black 1, 2, 3, 4, 5, 6, stripe 1, 2, 3, 4, 5, 6. And then you should be able to calculate the probabilities for each of these. What is a little bit easier with this one is that the probability for anything on the die is 1 in 6 all the way down, right? So we could put 1 in 6 for all 18 of the dice rolls in blue. But when you get the probabilities, you see this pattern that all 6 of these behave the same way, 1 in 24. Once we spin black, all 6 outcomes that started with a black land on 1/12. And then for the stripe, all 6 possibilities that started with a stripe give us a 1 in 24 chance, just like starting with a white. And we should be able to then change these fractions to decimals. If you divide 1 divided by 24 and round it to 3 decimal places, multiply by 100 to get the, round it to 100 to get the percent. Let's look at the individual problems now, the questions that are asked. When we read these questions, find the probability of landing on white and then 2. Do you see that I've highlighted that for us? White and then 2 has a 1 in 24 probability. Black, and then, so we'll start with black, and then we roll a 6. So it looks like that has a 1 in 12 probability. The white, and then even, it's a 2, 4, or 6. Do you see that we're getting this 1 over 24, but we're getting it 3 times? So what we'll have to do for this one is say that all three of these would work. Because if we looked at even and oddness, the probability of getting an even is 1 and 2. The probability of white was 1 and 4. And when we multiply those, we get 1 over 4 times 1 over 2, which is 1/8. When we add these up, we get 3 over 24, and that reduces to 1/8. Let's look at these others. This striped, let me go to another page where it's not all marked. If we do the probability of striped and less than 5, let me get a new page here so that it's not too marked up for us. So we're doing this one here, striped and less than 5. We'll start with the stripe, and less than 5 is going to be the 4, 3, 2, and 1. So striped and less than 5 would give us a 1/4 times, each of these was a 1/6, so 1 in 24, and since there were 1, 2, 3, 4 of those, we're going to add it 4 times. So 4 in 24, and that's going to reduce. 4 goes into 4 once, 4 goes into 24 6 times, so it's going to reduce to a 1/6. But notice another way I could have seen this is I could have seen that the probability of getting a stripe is 1 in 4, and the probability of getting less than 5 was 4 out of 6. And although I could reduce that before I started to multiply, I don't have to, because when they multiply, those are going to reduce, and I still get 1 and 6. So that's a way we could check the result. Let's do not striped and odd. The probability of getting something that's not striped, we'd have the black or the white, and then odd would be the 1, 3, and 5. 1, 3, and 5. Since these are all equally likely for the 1, 3, and 5, on white and then 1, 3, and 5, I've got this 1/24 for all three of those. And then the black 1, 3, and 5, those are each equally likely with one another, so 1 in 12. But I can see that the total will be 1 in, sorry, let me write that correctly, 1 in 24, 3 times, and then 1 in 12, 3 times, and we could add these two together to get the total. I'm going to leave that adding to you. You could add with your calculator, or you could reduce and then add, but you'll need a common denominator. Last one, we've got green and then odd. Well, what's the probability of that spinner landing on green? It's going to be, I don't see a green. So what's the probability of green? There's nothing that we would select. So the probability of green is 0. So the probability of green in any number is still 0 because there is no green. So that one is a quick, easy one once we understand the problem. Let's look at this next case. Suppose the probability that a new spark plug is defective is 1 in 24, and suppose that you buy 2 spark plugs. So for the first spark plug we pull out, it could be a defect or good. And for the second, again, it could be a defect or good. Writing the probabilities in, we'd have 1 in 24 for a defect, 23 and 24 that it's good. And then when we put that in for the second round, we can see that getting 2 defects in a row has a 1 in 576 chance of defect, and then a good would be 23 and 576. Good and then defect, 23 and 576. Good and then good again, 529 out of 576. So suppose you buy 2 plugs. What's the probability that both are defective? Both defective would be defect and then defect again. So we follow the 1/24th and then the 1/24th. And that probability is 1 in 576. Let's look at the multiple choice test. If we have this multiple choice test, the first question could be right or wrong, the second question could be right or wrong, and the third question could be right or wrong. Do you see how to write out, we've got 2 times 2 times 2, or a total of 8 outcomes in the sample space. And they're not all equally likely because we're more likely to get it wrong than we are to get it right, because the probability of being right is only 1 in 5. So when we write the probabilities in, we could get the sample space probabilities. So for a right and then right and then right, if we start with the first problem being right is 1 in 5, then the second probability, or the second question would be 1/5 and 1/5, or 4/5, 4/5, and then the third one would be 1/5, 4/5, 1/5, 4/5. If we multiply those, we get the total probability, and you could finish the bottom 4 also. And so if we multiply these, we'd have 1 over 5 times 5 times 5, 4 over 125, 4 over 125, 16 over 125 for the top 4, and so on. You just multiply 1/5 times 1/5 times 1/5 to get the final answer here. Let's look at this number block. I'm going to start by seeing what the different outcomes are. We could get an A, R, K, N, or S, and there's 3 A's, 1 R, 1 K, 1 N, and 2 S's. So the probability of each of those is different. The probability, let me see if I can move the paper up. There we go. Probability of an A is 3 in 5. An R, K, or N is 1 in 5 for each of those, and the S is 2 in 5. So I have the tree drawn to calculate the probabilities. I'm going to say the probability of an A for the first draw is 3 in 5. But what's the, notice that the probability of getting an A for that second draw is now that, let me go back and look at these numbers again. Now that one of these A's is gone, do you see that there's a total of 7 tiles left because we don't replace it? So there's 7 tiles left. Let me highlight this. This is without replacement. So what that means is I'm not going to put that N back in, or I'm not going to put the A back in. So when I go to draw the second one, there are only 7 in the denominator, and the numerator, if I already have one of the A's is gone, now there's only 2 A's left, so I'd have 6 out of 35. Let me talk you through that one more time. The probability of the A on the first draw is 3 in 5. But when I don't put that A back, there are only 2 A's left in the box, and there's only 7 tiles total. And I just noticed these should all be over 8, shouldn't they? Because there's, well, because there's 8 tiles total, so 3 and 8 and so on. So 3 over 8 times 2 over 7 would give us 6. Let me rewrite that to make sure everyone's got that. 3 and 8, 2 and 7, and I apologize I didn't catch that before I started filming this. So 3 over 28. And then let's make sure we can continue this. The probability of an A for the first one was 3 and 8. And then once we have an A, there's still 1 R left out of 7. So 3 and 56. And so on. A and then K. The first draw is easy. It's 3 and 8 for all of this first group, right? Because we started with the A, so that was a 3 and 8. But then after we have 1 tile gone, and it's an A, how many K's are left? 1. How many tiles are left? 7. After we have an A drawn, how many N's are left? 1. How many tiles are left? 7. After we draw that A, there's still 2 S's out of the 7 tiles. So you could reduce and multiply here to get 3 over 28. And then we could do the same for the draw when the R goes first, the K goes first, the N and the S goes first. Sorry about this slide with the numbers were not right on there. Let me know if you still have a question on that replacement. This next one is also without replacement. So let's look at this one more time. We could start by writing the branches. We could get an R, G, or Y, and then our second draw, again, an R, G, or Y. Notice that the first draw, there's 2 reds, 4 green, 3 yellow. So we have a 2 and 9, 4 and 9, 3 and 9 probability. But when we go to draw the second letter, there's only, once we've gotten an R, there's only 1 R left. So that's why this is a 1 and 8. There's still 4 greens, 3 yellows. Once we draw out a G, one of the G's is gone, and there's only 3 G's left. But there's still 2 reds and 3 yellows. So we'd have a 2 and 8, 3 and 8, or 3 and 8. And then finally, once we draw a yellow, one of those yellows is gone. We don't replace it. So our probabilities are 2 and 8, 4 and 8, and now there's only 2 yellows left, so 2 and 8. You could calculate those probabilities by multiplying, and then you'd be able to answer the different questions that are here. I didn't work out all the arithmetic here, but you should be able to continue that, and you should be able to change it to a decimal by dividing and then multiply by 100 to get the percent. Really quickly, this H and R, we're not going to draw a tree because it's such a big problem, but notice that we're not replacing in either H or R. We have 2 students chosen at random from a class of 30, so what's the probability that both you and your friend are chosen? Well, there's 2 ways to be favorable, so it could be you or your friend. So 2 out of 30, the first draw. For the second draw, if one of you has been chosen, and there's only one of you left, and out of the 30 students total, there's only 29 students left, so we would have 2 over 30 times 1 over 29. In the same way with the cards, there's 4 aces total out of 52. If you're not familiar with a deck of cards, there's one of each type of card and 4 different suits. So 1 ace times 4 suits gives us a total of 4 aces. So 4 out of 52 cards is an ace. And if we got the ace in the first draw, then in the second draw there are 3 aces left out of 51 cards total. Well, I hope that this helps you complete this sheet, and I hope it answers some questions about tree diagrams and about independent events and about replacement. If you have further questions, I hope that you'll let me know by either sending me an email or coming to visit with me in the virtual office.